Welcome. In this final lecture on the course of analysis of beams, we shall look at some practice problems on slope and deflection in beams. Practice problem 17 is stated as follows. For the given cantilever beam with distributed load, find the slope and deflection at the free end A. Young's modulus of elasticity is equal to 2 times 10 to the power of 5 megapascals and area moment of inertia is equal to 1 times 10 to the power of 8 millimeters to 4. You may now pause the video at this stage and resume when your solution is ready for verification and reference. Welcome back. There are two types of loads acting throughout the beam length, hence only one equation can be written for the moment and hence for the slope and deflection. We can therefore use the double integration method to solve for the unknown parameters. Let the coordinate system be assumed at free end A for convenience. Using the double integration method, the moment, the slope and the bending moment equations are written with the inclusion of unknown constants of integration C1 and C2. The boundary conditions are introduced, namely the slope at the fixed end B is equal to 0 and the deflection at the fixed end B is also equal to 0. The constants of integration are found out as C1 is equal to 33.33 and C2 is equal to minus 50.667. The final slope and deflection equations are hence written for later reference. Finally, the slope at free end A is found out to be equal to 0.00167 radians or 0.094 degrees, and the deflection at free end A is found out to be equal to minus 2.53 millimeters, minus indicating that it is acting in a downward direction. The beam loading diagram for practice problem 18 is drawn next. The flexural rigidity parameters are also given. It is required to estimate the deflection at the free end A of the cantilever beam. You may again pause the video at this stage and resume when it is ready for verification and reference. Welcome to the solution of practice problem 18. The coordinate system is assumed to be located at the free end A for convenience. By simple interpolation, the ordinate of the uniformly varying or the triangular load is found to be 15 times x minus 8 kilonewton per meter for a distance of x meters from the reference end A. Now, the equation of the elastic cover is introduced and the bending moment equation is written in the form of half range or singularity functions. We introduce the unknown constants C1 and C2 after integrating the moment equation once and twice successively. The boundary conditions are introduced, namely, both the slope and the deflection at the fixed end B are 0, thereby giving the value of the unknown constants as C1 equal to 730 and C2 equal to minus 5619.33. The final deflection equation is written and the value at the free end A is found out as minus 2.81 millimeters, minus indicating that the deflection is pointing in a downward direction. We now proceed to practice problem 19 and is stated as follows. Determine the deflection at the free end C for the overhanging beam ABC loaded as shown in the figure. Take Young's modulus of elasticity equal to 200 gigapascal and area moment of inertia equal to 13.5 times 10 to the power of minus 6 meters raised to 4. The given beam is drawn here for reference. You may pause the video here and resume when your solution is ready. Welcome back. The solution to practice problem 19 is shown here for reference. The reactions at A and B are found out by considering the whole beam in complete static equilibrium. Reaction at A is found equal to 3.75 kilonewtons and reaction at B is found equal to 9.75 kilonewtons, both acting upwards. Let us locate the coordinate system at the free end C so that positive x points to the left and positive y points upwards. You may note here that it is immaterial whether the coordinate system is selected at A or at C, but it is a matter of convenience. The differential equation of the elastic curve is now written for the entire beam, and the moment terms are added due to the various loads in the form of half range or singularity functions. Unknown constants C1 and C2 are introduced after performing successive integrations. Boundary conditions are added, namely, the deflection at both the supports is 0 to get the value of C1 equal to 9.8125 and C2 equal to minus 13.625. The final deflection equation is written for later reference. Finally, the deflection at the free end C is found out, and the value is 5.05 millimeters acting in a downward direction. The last of the practice problems, that is numbered 20, is stated as follows. For a beam loaded as shown in the figure, find the slope at points A and B and the deflection at points C and D. Also find the maximum deflection in the beam. The given beam is drawn here for reference. You may again pause the video here and resume when your solution is ready. Welcome back. Considering the beam in complete static equilibrium, we first find the beam reactions. We get reaction at B equal to 6.05 kilonewtons and reaction at A equal to 4.95 kilonewtons, both acting in an upward direction. Now, let the coordinate system be located at point B so that positive x points towards the left and positive y points upwards. The equation of elastic curve is written and the moment terms are added for the individual loads acting on the beam in the form of half range or singularity functions. Integration is performed once and twice and the unknown constants C1 and C2 are added. The boundary conditions are introduced, namely, the deflection at the supports A and B are both equal to 0. We hence get C1 equal to minus 47.029 and C2 equal to 0. The final slope and deflection equations are written with the values of the constants introduced for later reference. The slopes for the points A and B are therefore found to be 42.64 over flexural rigidity EI radians and minus 47.029 over EI radians respectively. The deflections at the points C and D are respectively found out to be equal to minus 136.103 over EI meters and minus 86 over EI meters, minus indicating that both are acting in a downward direction. For finding the maximum deflection in the beam, we equate the slope to 0. Simplifying, we get the location where it occurs as 4.8696 meters. Inserting this value in the deflection equation, we get the maximum deflection as minus 136.21 over EI meters. Minus sign again indicates that the deflection is pointing in a downward direction. The deflection curve is drawn with the values of slopes and deflections at important locations for reference. We hereby complete the final chapter on the course of analysis of beams. Hope you enjoyed the course. To conclude, it is very much possible that there may be some errors crept, knowingly or unknowingly, during the preparation of the course. Also, I sincerely apologize if the quality of the audio and or video are not up to the standards for some of the chapters, as this is the first digital course content I have prepared and uploaded as a part-time job with a lot of challenges and has taken me more than a year to realize. You are requested to kindly leave some comments for constructive feedback and possible corrections. Thanks for watching. Happy learning.